Last session, we stopped here with convolutional sequence-to-sequence learning. And then the idea was to replace the RNNs with CNNs. And for the encoder part, when you're encoding an input sentence, you needed to pay attention, or we shouldn't call this attention. You need to take into account not only the present and the past, but also the future, because the entire sentence is in front of you. And when it comes to the target language, the one that you want to translate to, you can call this part the decoder. You are not allowed to look at the words in the future. And the reason for it is actually what you want to do with translation. You're spitting out one word after another until you see the end of the sentence. So we had input sentence, target sentence. The target sentence was paying attention to the encodings of the input sentence, and then you are outputting your translation. So that was the idea of CNNs to do translation. And actually the model is simple and yet powerful. It's giving you one of the best results at that time. And as you can notice the pattern, there is this confusion when it comes to language of which architecture should we choose. Should we choose recurrent neural networks? Should we use LSTMs? Should we use recursive type of architectures and tree-based architectures? Should we use LSTMs, bidirectional LSTMs, or should we use convolutional neural networks? But one ingredient is always there. There is this attention mechanism that regardless of the architecture, you have that. And therefore, this paper came along and said, can we actually get rid of CNNs, RNNs, LSTMs, recursive neural networks, tree-based models, and only use attention? And it turns out that the method is actually really powerful. The idea worked. This is convolutional sequence-to-sequence, an ensemble of them for the task of translating from English to French. That one is giving you 41.29. And the transformer type of architecture is giving you competitive results. This is a slightly lower, but when you go to translating from English to German, that one is doing much better. So the attention alone is going to end up working, but there is some modifications that you need to make. One of them is attention mechanism is going to forget the ordering of your input sentence. Basically, it's operating at the set level. It's going to take as input a set of vectors. It's going to output a set of vectors. So it's going to lose the ordering. To bring the ordering back, you're going to have some positional encoding. And this idea is actually not new. We saw it when we were doing convolutional neural networks as well. Okay, perfect. So these positional encodings are going to end up being important. You can either learn them the same way that you learn word embeddings. You can learn positional embeddings, just set them to be trainable parameters, initialize them randomly, and let it be trained. Or you can just fix them, use sines and cosines. T is a low-dimensional signal. It's actually one-dimensional. And T, you can think of it as time here, which is the current token that you want to translate, or the current token in your input or even the output sentence. One idea is neural networks like high-dimensional stuff, high-dimensional vectors. They're not going to like time because it's low-dimensional. It's actually one-dimensional. The idea of these sines and cosines is to increase the dimension. Basically, you're turning a single time, maybe integer 1, 2, 3, 4, 5, 6, into vectors of a dimension that you choose. In this case, it's going to be D model. And that's how you're going to end up with a deterministic positional encoding. The sine, you're going to use it for the odd locations in your positional encoding vector. Cosine, you're going to use it for the even positions. And this 10,000 is just a big number for you not to be repeating yourself. So that's the idea with positional encoding, and that's how you're going to bring back position. You have your word embeddings, you add to them your positional embedding. Now you know which word is currently at which location in your sentence. The rest of it is the usual attention that we are used to. There is going to be query key value that you're going to generate out of multiplying your input sentence by a matrix or by 3 different matrices, then the query is going to look at the key and it's going to ask the question, how similar am I to this key? That's going to give you a scalar from negative infinity to positive infinity. You push that through softmax because you have a budget of 1 that you want to spread among your values. And then once you go to the next layer, it's just going to be a linear combination of your values. So the query and the key you're going to use to come up with the attention, and the attention you're going to spread among the values. And this is called self-attention. The reason for it is the query, the key, and the value are coming from the same sentence. So each word in your sentence is paying attention to itself. If the query is coming from the target sentence and the key and the value are coming from the input sentence, then that is the general attention mechanism. This is no longer self-attention. Your queries are paying attention to the input sentence. There is another thing that I need to mention, this multi-head. What do you mean? You're just going to keep repeating that query key value with their respective weights multiple times, maybe in this case m times, independently, and then concatenate all of them together. And this is what it means to be multi-head. We can think of it as being similar to group convolutions. So many people think that attention is all you need, but there are actually some modern architectures that replace the attention with it's a sort of multi-layer perceptron that is gonna mix the information channel-wise and position-wise. Position, I mean the position in your sentence. Channel, I mean the dimensionality of the embeddings. So it's gonna replace attention with such a simple idea, and then still the architecture works. So to be honest, attention is not all you need. The most important one is this feed-forward components. This one, if you remove it, it's going to significantly impact your results, the quality of your translation, or the quality of your language model. So actually, this feed-forward ends up being really important. So maybe this feed-forward net is all you need. The title is a little bit controversial, but that doesn't really matter. What you need to learn about is the transformer architecture here. And what is that doing? After these operations, you're going to end up with n vectors. You take each one of them and you push them independently through the same feed-forward network. You take each one of them independently, multiply by a matrix, add the bias, push it through ReLU, multiply by another matrix, add the bias. And the dimensionality of this operation, so basically you're going from D model dimension to usually 4 times bigger, and then you go back to D model dimension. And this idea is also really powerful. It's called inverted bottleneck. Our bottlenecks are usually we go from a high dimension to low dimension and then to high dimension. This is actually the reverse. We go from low dimension to high dimension and then to low dimension. And there are actually some modern convolutional neural networks that use that idea, going from low to high and then back to low. That is for self-attention, all of these, and the encoder part of your architecture. If you want to decode, you are not allowed to look into the future because that's actually what you want to predict. Therefore, this summation should be only up until t-1, the previous time step. And this you can achieve using masking. So when you are creating your attention matrix here, and if you notice this attention matrix is going through a softmax, if you make one of these values negative infinity, then through the softmax, that value is going to end up being 0 as you push it through the softmax. And as you multiply alpha by your vectors, for those n's that you set them to be negative infinity, the corresponding alphas are just 0, and therefore you are not summing up all the way to the end. And that's how you actually code it in practice, the masking idea. Just set this to be a very negative number. And that's why you see the word mask here. Any questions about transformers? So it's an assignment for you to watch that video, but now is a good time to ask questions. Was everything clear? Okay, perfect.